We're going to discuss boundary conditions on a stretched string. So first of all, let's just think about going from the nominal physicist's dream of an infinite string to a finite string which behaves in the same way as an infinite string. So let's think about some piece of the string which we've got here, and on the left hand side and on the right hand side we've got some form of boundaries. Now I'm assuming that we are only thinking about a wave travelling to the right, so on the left hand side we have to have some kind of driver, and on the right we have to have some kind of damper. Now on an infinite string, let's just think about what would be happening. So on an infinite string we would have our portion of string here, so here's the joining point at the ends, and then we would continue off down here like this, and continue on to the right like that. Now at this point we know that there is a tension in the negative x direction, that's on the left hand side, and on the right hand side we know there has to be a tension in the positive right direction. So now we can think about the driving and damping forces. So the driver, F, let's say dr for drive, is going to be, well, it's minus t because that's the force at the left hand side, but then we have to resolve that along the string, and so that's going to be d psi by dx, and I'm going to say that's going to be evaluated at x equals 0. So let me just notate that up here. The left hand side is x equals 0 and the right hand side is x equals L. Okay, we then have the damping force on the right, F, let's say dA for damp, and that's going to be capital T, that's going to be positive because it's pulling to the right, and that's also going to be d psi by dx at, now this time, x is equal to L. Now, we can just recall that the reason that we can resolve the forces along the string like that is simply by approximating sine x to be tan x, and then tan x is given by d psi over dx for small angles. Using the travelling wave equation, because this is a travelling wave, we write d psi by dt plus c d psi by dx is equal to 0. Quick consistency check, c has units of meters per second. That means that when we multiply d psi by dx by c, we'll end up with psi over time, which is exactly what we get on the left hand part. And we have the plus sign here because it is a travelling wave to the right, because that's going to the right. Okay, using that, that tells us that d psi by dx is equal to minus 1 over c d psi by dt, and we can substitute in, so we see that the driving force is t over c d psi by dt at x equals 0, which we have to find as z0, the characteristic impedance, d psi by dt at x equals 0. And the damping force, F damping, is just equal to minus z0 d psi by dt at x equals L. Now, these signs make sense. The driving force is where we're putting energy into the system, so that should be positive. The damping force, we're taking energy out of the system. So that's for mimicking an infinite wave. Let's just think a little bit about what happens when we have two strings that join. So I'm going to draw a thin string. If you want to, you can think of this as a piece of cotton, and I'm going to draw a fat string. So we've got Z1 on the left and we've got Z2 on the right, and of course these should actually be curved because we're going to have a wave travelling down them. These will meet at x equals 0. So at x equals 0, we must have, for continuity, minus t d psi by dx, let's put an L for left, and that must equal minus t d psi right by dt. So what we're saying there is that at the joining point, the gradient of the two strings must be the same. In fact, we could, if we wanted to, just say that the gradient must be equal. Sorry, that should be an x on the right-hand side. That shouldn't be a t there. That should be an x. We don't even need the factor of t, the tension. but I think it's maybe slightly more physically helpful. So now we have that psi L is equal to psi incoming plus psi reflected, and we have that psi t, the transmitted, sorry, psi r, the transmitted, with the wave on the right hand side is psi t, the transmitted wave. We note that psi I is travelling to the right, psi r is travelling to the left, and psi t is travelling to the right, assuming that our initial wave comes in from the left and travels to the right. So if we substitute this in and use the wave equation, so we substitute for psi L and psi R, and we're going to use the travelling wave equation again. And we're going to need to note that there will be a difference in sign between the reflected and the incoming wave. So when we do that, we have that minus t into d psi I by dx plus d psi reflected dr by dx is equal to minus t d psi transmitted by dx. Using the travelling wave equation, we find that minus the tension times 1 over c d psi I by dt minus 1 over c d psi r by dt. The minus sign comes because the reflected wave is travelling to the left. And we'll come to what that is equal to in a moment. I just want to notice that the speeds should be different on the left and the right. So I'm going to put a little c1 and a little c2 here on the diagram at the top. And so, of course, the speed that we're using in the travelling wave equation for the left-hand wave should be the speed on the left-hand side. And that's going to equal minus t divided by c2 d psi transmitted by dt. When we collect terms, we find that that means that z1 d psi I by dt minus z1 d psi r by dt is equal to z2. And now I'm going to take into account the fact that the psi t must equal psi I plus psi r. So I'm going to have a psi I by dt plus d psi r by dt. So I'll put this up here. I'll say at x equals 0, psi I plus psi r is equal to psi t. That's just a boundary condition that's saying that the junction stays fixed. Now, if we multiply out and rearrange, what you find is that you end up with d psi I by dt multiplying z1, that's on the left-hand side, minus z2 is equal to d psi r by dt multiplying z1 plus z2. And that in turn, I'm just going to go up here, implies that d psi r by dt is equal to z1 minus z2 divided by z1 plus z2 d psi I by dt, which we write as capital R, the reflection coefficient, d psi I by dt. From that, you can derive the fact that psi r at x equals 0, comma t, must equal r psi I of x equals 0, comma t. You can do that by integrating, or you can just argue that since the reflection coefficient is going to be time independent, the only way that we could get the condition on the velocities is to have the condition on the reflection coefficient. And then using the fact that psi t at x equals 0 is equal to psi I at x equals 0 plus psi r at x equals 0, that then gives us that that's equal to 1 plus r psi I at x equals 0, which is of course capital T. times psi I of x equals 0. And you can, if you want to, work out that t is equal to 2z1 over z1 plus z2. So we've been thinking mainly about resolving the tension along the string. We've noticed that you have to have the same forces at 2 points at the same point on the string in order to make the boundary conditions work. And from that we've derived the forces that you would need to drive a wave along a string and to damp it as if the string was infinite. And then we've gone on to consider how waves react when meeting a boundary. Of course, this is much more general than just waves on a string. It's true also, for instance, for light waves when they reach an interface. So this is why you get reflections off windows and you get transmission through windows. And all other waves have exactly this property, and it all depends on the characteristic impedance of the two systems.